haloalkanes. Okay, haloalkanes, which are also called halogenoalkanes. And I might accidentally say halogenoalkanes instead. Okay, haloalkanes. So haloalkanes, if you take an alkane, okay, for example, you take propane. You take propane, 3 carbons. Okay, and if I put a halogen, like a chlorine on there, that's now a haloalkane. So that is called propane because there are 3 carbons, and then the chlorine takes the name chloro, and it's on carbon 1, so it's called 1-chloropropane. And this is called a prefix because it's written at the front of the name, okay, prefix, and it's called 1-chloropropane. So again, if we take let's say just take propane again, but this time we put a Br, a bromine. It's a haloalkane. There's hydrogens on all those carbons. Again, it's 3 carbons, so it's propane. It's bromine, and we go bromo, and it's on carbon 2, so it's called 2-bromo propane. If we take again 3 carbons, but let's put a branch on, let's put another carbon on, and let's put an iodine, and there's H's on all of these, which I'm just not drawing them on. Okay, main chain is propane. Now there is an iodine and there is a methyl group, and you need to put the prefixes, you need to put them in alphabetical order. They are both on carbon 2, so it is called 2-iodo, 2-iodo, dash 2-methyl propane. So I comes before M in the alphabet, so it's 2-iodo, 2-methyl propane. Okay, and if you had fluorine, it would be called fluoro. So it's chloro, bromo, iodo, and if you had fluorine, it would be fluoro. Okay, in classification, this is called a primary haloalkane because the carbon that the chlorine is joined to is only joined to one other carbon. This would be called a secondary haloalkane because the carbon is joined to 2 other carbons. And this would be called a tertiary haloalkane because the carbon that the iodine is joined to 3 other carbons. So that's called a tertiary, careful with your spelling, tertiary haloalkane. Okay, now the main reaction of haloalkanes is nucleophilic substitution. Substitution is the main reaction of haloalkanes. Now first let's do, what is a nucleophile? 1L. A nucleophile, the definition is an electron pair donor. So it gives away a pair of electrons. So the most common nucleophiles is the hydroxide ion, like sodium hydroxide, and it has at least 1 pair of electrons, and that's called a hydroxide ion, and it can donate the lone pair of electrons. It has more than one. It has more than 1 lone pair of electrons, but we only show 1 lone pair. Another common nucleophile is just simply water. Now again, water has 2 lone pairs of electrons, but we just show 1 of them. So water molecule is a common nucleophile. Another common one is ammonia. Ammonia has got a lone pair of electrons, and so these are common nucleophiles that can react with haloalkanes. So let's have a look at the mechanism. Okay, let's have a look at the mechanism. So the name of the mechanism is nucleophilic substitution. So I'm just going to put nuc sub. Okay, now if you take a haloalkane, I'm just going to keep it quite simple. I'm just going to simply take this one, which is quite simple, which is called chloro 1 carbon. It's called chloromethane. Okay, chloromethane. Now, chlorine is electronegative. Chlorine is electronegative, which means that it's not sharing the pair of electrons in the covalent bond evenly. It is attracting the shared pair of electrons in the covalent bond. So it becomes slightly negative and carbon becomes slightly positive. So it is a polar bond because chlorine is electronegative. Okay, so along comes a nucleophile, okay, with its lone pair of electrons, and the lone pair of electrons are attracted, because opposites attracted to the slightly positive carbon. Now when you have a curly arrow, it's called curly arrow. A curly arrow shows the movement of a pair of electrons to form or break a covalent bond. To form or break a covalent bond. And it's called a curly arrow. And it's double-headed because there's 2 electrons moving. So the lone pair of electrons are attracted to the positive carbon because opposite charges attract. Now the 2 electrons in the covalent bond here, both electrons, the bond breaks and both electrons go onto the chlorine. Now this type of bond breaking is called heterolytic fission. This is the kind of bond breaking, so this is the bond, how the bond is broken to form a positive ion and a negative ion. Okay, to form a positive ion and a negative ion, and it's called heterolytic fission. Okay, so which is different to homolytic fission, which is in radical substitution. Right, so then what happens next? So we have now got, so we've got our carbon, so not kind of see, difficult to see, carbon with the 3 hydrogens. Okay, now the carbon is now joined to the OH. The covalent bond is joined to the OH like that. And now the Cl has got its electron back and the other electron as well. Cl minus. Okay, and this is the mechanism. What we've drawn here is the mechanism. And the mechanism is called nucleophilic substitution. Okay, right, and can you see you've got a minus charge here and you've got a minus charge there, so it's balanced. Okay, now this overall reaction is called hydrolysis. The overall type of reaction is called hydrolysis. And hydrolysis is when you break a bond. Hydrolysis is breaking a covalent bond with water or hydroxide ions. Okay, so the overall reaction is called hydrolysis. And if we wrote a chemical equation for this, then it would be CH3Cl, and if we do hydrolysis with sodium hydroxide, the overall chemical equation, then we would get the alcohol, methanol, and sodium chloride. Okay, so we're going from chloromethane to methanol. So it's a way of making an alcohol. Okay, right. So we need to know a little bit more about this. So if we were to compare, so this reaction, how could we work out what reacts? Let's get a piece of paper. What reacts the quickest? If we compare, so for example, if we compare chloroethane, okay, chloroethane with bromoethane, all hydrogens, with iodoethane, okay, which one will do this reaction the quickest? Okay, which one, if you put the hydrolysis, which one, like this, slightly negative, slightly positive, which one of these chemicals will do it the quickest? Okay, the fastest. Which one, right? So you need to know experimentally how to do this. So what you do is you take the haloalkane, just one haloalkane, okay, and you dissolve it in ethanol. Now you add ethanol because ethanol, the haloalkane is not very soluble in water, and the ethanol is just a solvent to help the haloalkane and the water mix. It's just a solvent to help mixing of the halogen alkane. You do that first, okay? And then you add silver nitrate. You've got silver nitrate solution. Okay, you need to warm it as well. Temperature probably about 50-60 degrees. Okay, and we're going to use silver nitrate solution. Okay, silver nitrate solution. So I'm just going to explain why. So if you have your halogenoalkane, so let's take chloroethane for example, right? And you add water, it's a hydrolysis reaction, okay? And you get your ethanol, the Cl bond breaks, and you get ethanol, and then you get HCl. Now a HCl in water is H plus and Cl minus, okay? So you're releasing Cl minus. So if we want to see which one of these does it the quickest, does this react the quickest, this one or this one, we're going to be releasing a halide ion. We're going to be releasing a halide ion. Cl minus, we're going to be releasing Br minus, we're going to be releasing I minus. So what we do is we time how quickly a precipitate is formed. Because remember, when you add silver nitrate and a chloride ion, as soon as a chloride ion is formed, it will form a white precipitate of silver chloride. Whereas the bromide ion will form a cream precipitate. And then do you remember the iodide ion forms a yellow precipitate of a yellow one. Just squeeze it in there, yellow, okay, yellow, right? So what you do is you put your haloalkane in some ethanol and you warm it in a beaker of water to about 60 degrees. Then, and you've got all three in a test tube. You've got that one in a test tube, then you've got another test tube with the bromos in there, and then you've got another test tube with the iodos in there, right? So you've got 3 test tubes, and they're all warm in beakers at 60 degrees. And then you add silver nitrate at exactly the same time, and you start the clock. And the first one to form a precipitate will have reacted the quickest. So the first one to form a precipitate, whether it's chloride, bromide, ion, will be the quickest. Okay, so time taken to to form a precipitate. And that's practically how you do it. Okay, but let's have a look which one is actually going to react the fastest. Can we predict? Right, but there's two things happening. First, the nucleophile is attracted to the slightly positive carbon. So it depends on the bond polarity. Okay, which one of these bonds is going to be the most polar? Is that the most polar bond? Is that the most polar bond? Is that the most polar bond? CCl is the most polar out of those three. So it's going to be able to attract the nucleophile the best. So able to attract the nucleophile the best out of the three of them. Okay, the might be the easiest. But that's only part of it, because you've got to attract the nucleophile and then you have to break this bond. Okay, so breaking a bond is called the bond enthalpy. It's talking about the strength of the bond. Okay, so if you have to break this bond, then you want it to be a weak bond, because a weak bond will break easier. So which bond, CCl, CBr, Ci, which bond is the weakest bond? Okay, so the weakest bond is the Ci bond, because iodine is the largest of those three, the largest halogen. So it can't get in close to the carbon, and that's the weakest bond. Okay, so there's two competing factors here. CCl is the most polar and can attract the nucleophile the best. Ci is the weakest bond, and that bond will break the easiest. So which factor is the most important? Which factor makes the biggest difference? And it's the Ci, the bond breaking, the strength of the bond is the most important factor. So the iodo compound will react the quickest. That will be the fastest, because it has the weakest bond. The Ci bond is weaker than the CCl bond. Less energy is needed to break that bond. Less energy is needed to break the bond. Okay, break the bond. So if we do this experiment, the precipitate that will form first is the silver iodide, the yellow precipitate, silver iodide, because it is the weakest bond. Okay, and that's called hydrolysis.